Hello and welcome, I'm Diego Ontiveros, and in this video I'll walk you through how to install and use MXgap, a Python program I developed. Recently, we published a paper introducing the MXgap program, which focuses on developing machine learning tools to quickly predict the bandgap of MXene compounds. The idea behind it is quite simple. Starting from a low-level calculation, like for example PBE, the program takes the geometry and optionally the PBE density of states, and then uses pre-trained machine learning models to predict the bandgap of these MXene compounds. In this case, it estimates the PBE0 bandgap, which was the value that was targeted to train to, which provides a much closer representation of the true bandgap value. For now, the program is mainly designed for VASP outputs, although there are some workarounds to use other types of outputs, as I'll show you later on.
Okay, so the installation process is actually quite easy. I will do here the tutorial for a Linux environment, but the process is exactly the same using a Windows or Mac operative system. So the installation can be managed through the Python package indexer installer, so the pip installer, by doing pip install MXgap. But I would recommend to first create a conda environment so that the dependencies of this package are well managed and there are no dependencies errors or anything. So this would be a recommendation. To do that, you can first create a conda environment by doing conda create. You give it a name, for example, MXgap or whatever you want to call it, and a Python version. In this case, I would choose 3.12, which was the one that was developed during the MXgap program, but it can be anyone from 3.9 upwards. So this will create the initial environment for the program. And once it's created, you can activate it with the code here so that now the name appears in between brackets right here. So now that we have our environment, now we can install the package through the pip installer. With that, it will install all the dependencies and all the packages that it needs, and also the different machine learning models that have been trained will come also through this installer. Okay, so the installation has finished. Now the MXgap program is ready to use to test if everything is working correctly. You can just run the command -help to see if it outputs a bit of the information of the program and all the things that you can do. And another way to install the package is through installing all the source code from the GitHub repository. And to do that, we can clone the directory with the link from the GitHub repository, and that will create a clone of the full repository and all the source code examples and so on. All the models will come also installed here, and now we have the MXgap folder, and here it's all the source code already. If you want to install this, you just need to go to the directory of the code and pip install that to install the package through the source code that you have developed. But in the end, it will be quite the same as doing it through the pip installer.
Okay, let's go to the usage of how can we use this program and package. And there are two main ways to do that. One is through the command line, through the terminal itself, and the other one is through Python scripts like a Python file or a Jupyter notebook, and use it as a Python module, essentially. So let's go to the first one through the command line. Just make sure first that you are in a folder where you have your outputs of your VASP calculation. Especially we want here the concard file and the doscard if we want to include also density of states information, which is good since it improves the quality of the prediction. So one way to just basically run the prediction using the models is just to, once you are in the folder of your outputs, just run the MXgap command, and this will select some default model. In this case, it's the combination of a gradient boosting classifier and the random forest regressor, and it will use that to give you the classification and the regression prediction. So here we have that it predicts a semiconductor to be the material, and then a bandgap of 1.96 electron volts. So it will give you this prompt in the terminal, and also it will create an information file with essentially the same information that has been given. So if you want to specify a bit more the files that you want to pass to the model, in this case, imagine you have another name for the concar and doscar files, you can do that by using the F flag and specifically writing the names of the concar and doscar files. For example, if you have another names or something. In the meantime, if you want to select other model, you can do that with M flag. Later we will show an example. So if you do that, it will be the same, but you can control a bit more the name of the files that you choose. Otherwise, if you don't put this, it will search for concar and doscar, and if they are not found, it will give you an error. So if you want to choose any other model with the L command, the L flag, you can see at the list of all the available models. We have classifiers and different type of regressors for the prediction of the bandgap. And here you have divided in the ones that use density of states as an input and the ones that do not. So these ones do not use the density of states, so they do not require as much information, but the problem is that the results are not as accurate or as precise as these ones right here. So by default, it would choose, as I said before, the combination of the classifier and the regressor, the best model that we have, but you can choose any other model if you change the M flag right here and put a classifier. So for example, the gradient boosting classifier plus the random forest with only gap, which it's actually the best model right here, but it's just to see the other way to put it. And you can specify it here. You can choose both models, a classifier and a regressor, using the plus operator between them, but you can also choose either one of them. So for example, just a classifier, and it will give you the results for only using the classifier, or the regressor itself. Of course, it does not work because I forgot the only gap, and it will give you the results for the regression. So if you want to try any other model, you just write in the model flag. Okay, another thing we can try with the output is to pass the P flag, which will also give us the classification probability. So when the classifier predicts a number, it has a degree of certainty in this prediction. You want values close to 1 in this case, or to 0 if it's a metallic label. So this will tell you how the actual value between 0 and 1 of the prediction for if it's metallic 0 or semiconductor 1. In this case, we can see that since it's very, very close to 1, the model has very high confidence that this is actually a semiconductor. So this is just giving you the probability of this number being correct, more or less. So if you want to explore any other of the configuration that you can use, you can just do the H command to have a bit of all the different flags that you can pass. So for example, if you want to specify the output or where the results are written, you can do that with the O flag or the verbose flag to specify if the outputs are written in the screen or the file, in both, or none of it, you don't want any text, and so on. The other way to use the program and to interact with it is through Python scripts or a Jupyter notebook. And for that, we created a Jupyter notebook as a tutorial to see different stuff you can make it with it and how to work with that. The tutorial notebook, you can find it in the repository or where the source code is hosted in GitHub. But I will show you here just a basic example. So Just to get started, to do the same as you would do in the command line to run a simple prediction of the bandgap given the BASP outputs, you just have to import the run prediction function from the MXgap module, and then use the path and the models that you are going to use. In this case, the path will be the path that the file is in, and the model, the best model, which you can define by explicitly putting the model that you want, as we saw before in the command line phase. Or if you want the best, you can put literally best or default to select the best performing model. And then you run the prediction by running this command with different arguments. If you hover over this function, you can see again all the different arguments that this function takes, and the values that these arguments can take, and different examples. So that's to that. And this will give you the prediction in the variable. It will return the prediction, but also it will print the results in the screen, also in the report file that it has been created. For example, you can also have a look at the model list to get all the models. For that, again, we suggest, and I recommend, to have a look at the GitHub repository, where you have more information there. You can have a deeper look into all the different models, all the different tags, what do they mean, and so on, and have a better understanding. So one nice way to use this program is to screen a lot of different MXene compounds. In this case, you should have like a for loop for all the different paths where your calculation has ended, and then run the prediction for each of these folders with all the results to get the prediction from the model, and then you get a nice screening with the MXgap program, which is what you actually use that for in the paper. When interacting with the program through the Python scripting, you can get a bit more in depth in the programming, not only in the prediction, but also you can get, for example, different functions to get the features of the MXene that you have, that are the ones that are going to be passed to the machine learning model. So, for example, you can get the structure and periodic table array, which is the features corresponding to the structure and the elements of the MXene, and also the one that is used to get the density of states information. So as I mentioned before, the program is thought for BASP output calculations, but if you know how to handle different post-processing tools, it's quite easy to, from another program, like for example MXenes or CP2K or so on, extract the necessary information to pass to the models and do the prediction itself. So for that, in the point 4 here, I put an example of how would I do that for different for a MXenes program. And in this case, it's quite simple. We are going to use a combination of existing tools that the program itself gave us and different programming. In this case, I read the geometry in with the function to get the elemental array. This can be done since all the geometry is processed through ASE, and ASE can read a lot of different types of geometry from different types of programs. And the one that will require a bit more post-processing is the density of states. In this case, we have to ourselves read the density of states, extract the ones that we are the parts that we are interested on, and finally get the bandgap and band edges, make the histogram, and create ourselves the DOSCAR, or the density of states array, that then has to be passed to the prediction from data function that allows us to make this prediction from other types of program. And finally, another tool that I implemented in the MXgap program is the structure class, which is basically inherits from the ASE atoms class, but in this case has some extra functionality to accommodate the MXenes family of materials. So in this case, it's thought for playing with MXenes in a much easier way, and has some nice functions to quickly get the positions of the different MX and termination atoms, to get the stacking and hollows, to add some termination in a specific positions. So it has some this extra nice functionality that works and integrates quite well with MXenes. If you want to have more information about the models themselves, how we train them, the accuracy and prediction that they present, I suggest you have a look at the ACS Catalysis paper where we publish all these results. And there you can also find the database that we use to train these models and much more information about the whole project. Also, I would suggest to have a look at the MXgap GitHub repository where you will find more information about the source code, examples, and much more in-depth information for the program itself. And finally, if you have any questions, you can directly address me at my email here. And yeah, thanks for your attention and see you on the next one.